All right, number 9 is one of those problems like the ones I assigned the first day where you generate the formula that applies. So in this problem, you have, it says that an oil drop weighs 1.8 times 10 to the negative 15 newtons, and it's suspended in an electric field of 6.5 times 10 to the third newtons per coulomb produced by two plates that are 4 centimeters apart. What is the charge on the drop? So if I draw this, I have two plates. So I've got a plate here, and then I have a plate here. So what is being described here is the Millikan oil drop experiment. And let's see, what is the charge on the drop? So it's suspended in an electric field produced by two plates. Now, if I have an oil drop in this, so if I put an oil drop, then for it to be suspended, then the forces on this have to be balanced. So what that means is that the weight of the drop has to be balanced by the electrostatic force. All right, so there's my picture. This would be the weight, and this is the electrostatic force. Now it says, what is the charge on the drop? It's not really saying whether the charge is positive or negative. To solve this, I can at least get the value, because if it's a positive charge, then I know that the electric field would be in this direction. If it's a negative charge, then it would be in the opposite direction, because the way you can tell the direction of the electric field is the electric field is in the direction of the electric field is in the same direction as the force if it's a positive charge, right? So I'm just going to assume it's positive here. I'm just getting the value of the charge. So here's the picture. So what we have here is I know that the electrostatic force in this problem has to equal the weight, and they give me the weight in the problem. So I'm going to write that as my F. So my F in the problem is 1.8 times 10 to the negative 15 newtons. Also, they say that the plates are 4 centimeters apart. So 4 centimeters apart would be 0.04 meters. We need it to be in meters. So if we do need this, this will be our R. So I'll put that down also. So the R is 0.04 meters. And the charge that we're solving for would be the test charge. The source of the electric field are the two plates. Now actually, if I'm putting in the charge of this, then would have to be plus. So that plate would be plus, and this plate would be negative. In order to have an electric field in a direction that is up, the electric field is going to be away from the positive plate and towards the negative plate. So let's see what else. It's suspended in an electric field of, and they give us the value of that. So the electric field is 6.5 times 10 to the third newtons per coulomb, and the unknown in the problem is the Q, the test charge. So those are your facts. So I can see there that, remember this, yes? No, well, there's no radius here. This is just the separation between the two plates. All right, so it's not like 4 centimeters. That's not the diameter of anything. It's just how far apart the plates are. So those are our facts. So if you have F, E, V, and W, those are the four that I can create a formula with those four. And the big four here are, well, the two involved in this problem are F and E. So I know that F is KQ QO over R squared, and E is KQ over R squared. So the R part of this problem isn't even going to be part of the answer. I'm going to have that in order to make the bottom two equal, I need to multiply the top by QO on the right side. So if I do that, then I do the same thing up here. Now that these two are equal, okay, because they both have R squared, they both have KQQO, then now that they're equal, I know that these are equal. So this is now my equation that I'm going to work with in order to solve for the unknown. So if I rearrange that equation to solve for QO, I just need to move the E to the other side. And that's another way to check to see if you did this part correct, because I know my answer for QO should be in coulombs. If I don't get coulombs moving the E down here, then I must have done something wrong. So the QO is going to equal F divided by E. And so the force is 1.8 times 10 to the negative 15 newtons. And I'm going to divide that by the electric field intensity, which is 6.5 times 10 to the third newtons per coulomb. So I can see here that my Newton will cancel with my newtons, and the only unit that I have left is coulomb in the denominator of a denominator. So my answer will be in coulombs. And if you solve this, you end up getting, for your QO, you end up getting, what did I have, 2.77 times 10 to the negative 19. So 2.77 times 10 to the negative 19 coulombs. All right. Any questions with that? Now, that answer really doesn't make sense knowing that what we know about an electron, that the charge in an electron is 1.6 times 10 to the negative 19 coulombs. So this is somewhere between 1 and 2 electrons, and you can't have like a half of an electron or a quarter of an electron. So I got this number just by randomly making numbers here for what the electric field intensity would be and what the force would be. But if this were actually done, if this Millikan oil drop experiment were actually done, then I should get for an answer 1.6 times 10 to the negative 19 coulombs, or 3.2 times 10 to the negative 19 coulombs, or 4.8, some multiple of what the charge is on one electron. Right? Any questions?